Chemical engineers. Chemical engineers work in all sorts of jobs. Chemical engineering applies to nearly every field. Some engineers research new forms of alternative energy. Others improve rate processes for chemical plants. Many engineers synthesize new chemicals and transform existing ones. Often, chemical engineers try to solve major problems. For instance, some engineers develop desalination methods. Desalination will create fresh water where it is needed. A current chemical engineering project involves pharmaceuticals. Its engineers want to create a special computer chip. The pharmaceutical chip will provide a controlled drug release. As a result, people will not need to take medicine regularly.
Two, E_Morgan@chematronlabs.com. From S_Wiley@chematronlabs.com. Subject: Lab cleanup. Eric, someone forgot to clean up the lab yesterday. Could you organize it and clean it? There are some test tubes in the sink. Please clean them and then rinse them out with a wash bottle. Then organize the volumetric flasks by volume. They belong in between the beakers and the Erlenmeyer flasks. Please place the pipettes and burettes in drawers. Next, make sure the graduated cylinders are orderly. They are currently scattered around the counters. Also, put all the funnels in a cabinet. Finally, please look for a pestle around the lab. Our mortar and pestle set is currently incomplete. This mess is unacceptable. Please remind the staff to clean up after themselves. Thanks, Sandra Wiley.
Our products. Hot plate. Our hot plate's burner is 13.5 centimeters in diameter. Its temperature ranges from ambient to 350 degrees Celsius. It also comes with an electric thermometer. Desiccator. Our desiccator remains sealed at most temperatures. Under certain temperatures, it can hold a full vacuum. Balance. Our electronic balance can display weights in multiple different units. It also features USB connectivity. Stirring rod and dropper set. The basic set includes 4 stirring rods and 4 droppers. Both items are made from treated glass. It also comes with a stainless steel spatula. Tongs and forceps set. The basic set features 3 stainless steel tongs of various sizes and 3 pairs of curved forceps for smaller objects.
Lab safety procedures. This lab contains several hazardous substances. All employees must follow these guidelines. Wear protective clothing at all times. Do not enter the lab without goggles, gloves, and coveralls. Workers should also wear respirators around toxic fumes. Please work with hazardous chemicals beneath a fume hood. If chemicals make contact with your eyes, wash them immediately. Each lab has 2 eye wash stations. After rinsing the affected eyes, seek medical attention. Additional precautions exist in case of a fire. Workers should store flammable chemicals in safety cans. They should also memorize fire extinguisher locations. Smoking is forbidden inside the lab.
Symbol equals. Interpretation is equals comes to. Examples 1/2 equals 0.5. Symbol plus. Interpretation and plus add. Examples: A plus B equals C. Add A and B to get C. Symbol: minus. Interpretation: minus, less, subtract. Examples: A minus B is C. Subtract B from A to get C. Symbol: times. Interpretation: times, multiplied by. Examples: A times B equals C. A multiplied by B is C. Symbol: divided by. Interpretation: over, divided by. Examples: A over B is C. A divided by B equals C. Symbol: 2,400. Interpretation: 2,400 or 2,400. Example: We spent $2,400 on lab equipment.
Conversion between number types. Quantities are presented in multiple ways. For example, take the decimal number 0.25, which is a partial number and can also be expressed as a percentage. In this case, it would be 25%. Percentages express a certain amount out of 100. Additionally, this quantity can be a fraction, 1/4. A whole number can combine with a fraction. For instance, the mixed number 2.5 equals 5/2. It is easy to convert between number types. Converting decimals to percentages is easiest. Simply move the decimal point right 2 places. Converting percentages to fractions is also quite simple. Just place a percentage over 100, then reduce the fraction as much as possible.
The scientific method. The scientific method is a way of evaluating the world. It begins when a scientist makes an observation. The scientist's observation may inspire a question or problem. Then, the scientist forms a hypothesis to explain it. If the hypothesis is testable, the method continues. Next, the scientist designs an experiment. Experiments have experimental groups and control groups. An independent variable changes in the experimental group. The control group, however, does not change. Scientists repeat the experiment many times. Then, they analyze all of the results. The results either support or discredit the hypothesis. Based on the result, scientists form a conclusion about the hypothesis.
Employee Manual. Number conventions. Aurora Labs employ scientists from around the world. As such, agreeing on numbers is important. We must be certain that we understand each other. Small rounding errors will waste resources. If numbers are squared when they should be cubed, disaster may follow. Following our numbering conventions will prevent problems. Express all integers using scientific notation. Significant figures. Write numbers to the thousandth place. Add trailing zeros if necessary. Exponents. Use superscript numbers to multiply numbers to the nth power. Order of magnitude. Include a note for others if you alter a calculation scale. Include leading zeros in handwritten calculations.
Abstract. At Chemical Labs, we performed an experiment to address multiple problems. Over the previous year, our plant's plastics production declined. Over time,
the amount of waste climbed. The plant's level of output began to fluctuate. Meanwhile, the cost of production rose significantly. We needed to stabilize production, so we decided to increase input by 50%. The increase briefly caused output to expand by 20%. However, after a week, it shrank again. The amount of waste, however, did not decrease. As a result, the value of the plant plummeted. In future experiments, we will identify where the waste occurs.
Mark, I need you to produce some graphs. We have a table showing last year's production rates. The rows indicate rates and the columns indicate months. Please make 2 graphs showing the table's information. Make both a bar graph and a line graph. I will decide which to use later. Both graphs should show rates along the y-axis. The x-axis will show amounts of time. We also need to display average chemical production times. Create a pie chart to show them. Be sure to include a legend explaining it. Finally, compare quantities and production times using a scatter plot. Thanks, Olga.
Our scales precisely measure weight and mass. We calibrate our scales carefully to ensure accuracy. We will also calibrate them again for free. Our featured scale, the PS90, is an analytical balance. It can measure masses as small as milligrams. The balance features a glass enclosure surrounding its scale. The enclosure prevents wind and dust from affecting measurements. The PS90 even regulates temperature within the enclosure. Temperature regulation prevents air currents from forming inside the enclosure. The PS90's default measurement setting is metric. However, it can easily convert grams into ounces. Alternatively, it can give readings in kilograms or pounds.
Intro to Physical Science. Chapter 2. Measurements. People can measure quantities in many different ways. For instance, there are 3 systems for measuring temperature. One temperature system is the Fahrenheit system. The Celsius system also measures temperature, but does so differently. Water freezes at 32 degrees Fahrenheit and 0 degrees Celsius. However, kelvins also measure temperature. 1 Kelvin equals 1 degree Celsius. However, kelvins use a different scale. The Kelvin scale begins 273 degrees below the Celsius scale. Simple equations can convert units between the 3 systems. Different measurement styles even exist within single systems. The metric system measures volume in liters. However, it also measures volume in cubic centimeters. A cubic centimeter is equal to 1 milliliter.
Measuring quantities. Chapter 1. SI base and derived units. The SI system features 7 base units and many derived units. Base units are not combinations of other units. Derived units, however, are based on other units. For example, a mole is a base unit. Moles measure amounts of a substance. Molar mass, conversely, is a derived unit. Molar mass measures mass per mole. It is derived from moles and kilograms. The following are some other derived units. Name, Newton. Measurement, force. Base units, kilograms, meters, and seconds. Formula, 1 kilogram by meters by square seconds. Name, Pascal. Measurement, pressure. Base units,
kilograms, meters, and seconds. Formula: 1 kilogram divided by meters by square seconds. Name: joule. Measurement: energy. Base units: kilograms, meters, and seconds. Formula: 1 kilogram by square meters divided by square seconds.
Gina's Engineering blog, posted May the 17th by Engina-Ear227. Problem solving. Sometimes solutions to problems are hard to find, so I developed a procedure for solving difficult problems. First, I learn more about it. I recommend conducting a complete analysis of the problem. Often, a complete analysis will reveal alternate approaches. Then I choose a method of attack. If it fails, I repeat it in an iterative fashion. However, I change the approach slightly with each iteration. Most iterations include the application of several old approaches. If none of the approaches work, I redefine the problem. Then, I repeat the process with the redefined problem. Sometimes, a problem requires a synthesis of approaches. Keywords: problem solving, analysis, solutions.
Intro to Chemistry. Classifying matter. Scientists have dozens of ways to describe matter. For instance, scientists classify materials based on their characteristics. Homogeneous materials have characteristics that are uniform throughout them. Conversely, the characteristics of heterogeneous materials are just the opposite. For example, salt water is homogeneous while wood is heterogeneous. Matter is also classified by its phase. Phases are another condition that separates homogeneous and heterogeneous matter. Scientists also classify materials by how easily they separate. Substances are materials that cannot separate by physical means. However, physical means will separate mixtures. Finally, scientists classify matter by the types of molecules in them. Elements are substances that share the same atom type. Compounds are substances with more than one type of atom.
Chemical engineer. Position available. Chemtech Inc. is looking for a dedicated chemical engineer. Candidates should have expertise in chemical engineering. We are seeking personnel with the best abilities on the market. Applicants with at least 10 years of experience are preferred. Additionally, preference will be given to applicants with graduate-level degrees. Ideal candidates will be goal-oriented team players. At Chemtech, we value employees who focus on tasks and demonstrate commitment. We also appreciate employees with critical thinking skills. Much of the work at Chemtech involves making logical deductions. However, here at Chemtech, we also respect creativity. We seek workers who are innately curious about the world. We find that curious workers excel at innovative thinking. Out-of-the-box thinking is what made Chemtech as successful as it is. If you're interested in joining our team, apply today. Please email us your resume at hr@chemtechinc.com.
www.central-university.edu/chemeng.xml. Central State University, Department of Chemical Engineering. Central State's Chemical Engineering Department offers both postgraduate and undergraduate programs. Chemical engineering is a vast and profitable field of study. Chemical engineers use chemistry to solve problems in various areas. Truly, our graduates are devoted to providing better living through chemistry. Our bachelor's degree program will teach students the basics of chemical engineering. The program will thoroughly prepare students to pursue graduate-level studies. The program's first year will introduce students to basic concepts. Students will take classes like organic chemistry and fluid mechanics. Then, chemical engineering students will explore more difficult concepts in chemistry and engineering. A few prerequisites are required to enter the program. Students must take introductory physics and biology courses before entering. Additionally, students must take a calculus course during their first semester. The Chemical Engineering Department also offers master's degrees and PhD programs. Our doctoral program completes a student's mastery of chemical engineering.
Chapter 1: Classifying Data. Statistics is the study of methods for organizing and analyzing raw data. A complete set of data is called a population. When a population is too big, statisticians take a sample. Samples are small portions of a population that represent the whole. There are three basic ways to describe sets of data. The easiest way is by its range. The range is the difference between the data's largest and smallest numbers. Another way to describe data is by its central tendency. A central tendency is measured as a mean, median, or mode. The mean is the average value of the data. The mode is the number that occurs most frequently. The median is the center of an organized data set. Finally, a data set can be described by its variation. A set's variation is measured in deviations, mean absolute deviations, and variance. A deviation is the difference between a number and the set's mean. The variance is the standard deviation squared.
Engineering Essentials, Chapter 4, Accounting. UAE, Universal Accounting Equation. Engineers often have to monitor quantities in a system. The proper term for monitoring a system's quantities is accounting. The most useful tool for accounting is the UAE, Universal Accounting Equation. The UAE applies to both open systems and closed systems. However, it can only be used on extensive quantities. Intensive quantities are impossible to account for. The equation is final amount minus initial amount equals input plus generation minus output plus consumption. To use the equation, engineers must define the system and an amount of time. The time period plays an important role in determining the equation's variables. In a way, the equation is very simple. However, it is not just about subtracting the initial and final amount. To find the system's accumulation, an engineer must consider variables like generation and consumption. These define the quantities the system creates and destroys. Using algebra, engineers can calculate a variable based on the others. The simplicity of the equation makes this process very simple.
Effects of Filter 2860 on Flow Rate by Simon Ortega, chemical engineer. At Chemtech, we are currently upgrading our filtration systems. The previous system was old and outdated. The primary goal of this task will be the replacement of filters. We will install new filters on our tank's inlets and outlets. The 2860 filters were designed to not interfere with rate processes. They are very efficient with liquids with low viscosity. The flow rates of low viscosity fluids dropped only 1.4%. The flow rate should improve as we test the filters further. Unfortunately, the filters do impair the rates of high viscosity fluids. The resistance between the filter and fluids slows them considerably. When the fluid's driving force meets the resistance, pressure builds. Thus, if the flux falls too much, the system could explode. We are currently working to fix this design flaw. Until then, we will not replace filters on high-viscosity fluid systems.
Hydrogen. Hydrogen is the most basic and abundant element in the universe. The atomic number of hydrogen is 1. An electrically neutral hydrogen atom has 2 subatomic particles. A hydrogen atom has 1 proton and 1 electron, but no neutrons. Only the nuclei of hydrogen isotopes have neutrons. A single proton is also a hydrogen ion, since hydrogen ions have no other particles. The most common form of hydrogen does not have a neutron. In fact, standard hydrogen atoms make up 75% of matter in the universe. This kind of hydrogen commonly forms into diatomic molecules. Hydrogen has a total of 7 isotopes. However, only 3 of them are stable and common. One isotope of hydrogen is known as deuterium. Deuterium nuclei have a neutron and a proton. As such, the mass number of deuterium is 2. Deuterium is used in chemistry to form a variety of compounds. For example, heavy water is water with deuterium instead of standard hydrogen.
www.heliosec.com/FAQ. Helios Solar Energy Company. Frequently asked questions. What is solar energy? Solar energy is a way to take advantage of solar radiation. Its applications depend on the frame of reference. People have used solar-based heat for thousands of years. However, we have just begun using the sun's power to generate electricity. The energy quality and energy efficiency of solar power is constantly improving. What varieties of solar energy are there? Photovoltaic cells can convert solar energy. In this process, sunlight knocks electrons off the cell's material. This creates electromagnetic radiation. That energy then transfers into electrical wires. Another type of converted solar energy is called solar chemical energy. It resembles photosynthesis in plants. Such processes use sunlight and chemical reactions to release kinetic energy. How is solar energy stored? People often conserve solar energy in reservoirs as thermal energy. Thermal reservoirs are insulated to maintain their contents' potential energy. Later, people can harness the stored potential energy to produce work.
The class begins with an examination of atoms and subatomic particles. Following that, we will discuss the periodic table. We will cover element symbols and the table structure. The class will discuss the significance of its periods, groups, and blocks. Each student will give a presentation on an individual element. After covering the periodic table, we will observe how it reflects atomic structure. In this section, the class will review electron configuration. Students will analyze the contents and locations of electron shells. We will discuss measurements of atomic radii, and students will study the details of electron affinity. Afterwards, they will calculate the amount of ionization energy required to move electrons. Discussions about electron configuration will lead to VS-EPR theory. Here, we will learn about valence shells and their electrons. Then, we will discuss how repulsion between valence electrons can shape molecules. Finally, we will discuss how to find this information in the periodic table.
Intro to Chemistry, Chapter 4, The Periodic Table. The periodic table organizes elements by their atomic numbers. It also organizes them into groups with similar properties. These groups are organized into columns. Some larger regions of the table feature general similarities. For instance, the right side of the table features non-metals. The center and left side of the table presents metallic elements. The two are separated by metalloids, which only resemble metals. The leftmost column of the table consists of alkali metals. These metals are soft, silver, and shiny. The next column to the right features alkali earth metals. The next 10 columns are the transition metals. The transition metals include the lanthanides and the radioactive actinides. To the right of the transition metals are the post-transition metals. Chalcogens, such as oxygen, are located to the right of them. The next column has halogens. The table's final column holds the inert gases. These are also called the noble gases because they don't usually react with other elements.
The laws of chemistry. Chemistry features many laws. For example, the law of chemical combination describes compound formation. Similarly, the laws of thermodynamics describe the transport of heat and work. This list features other laws which address more specific interactions and circumstances. Avogadro's law. Under constant conditions, gas samples have equal molecular quantities. Boyle's law. At a set temperature, gas pressure and volume correspond inversely. Charles's law. At a constant pressure, gas temperature and volume are interconnected. Dalton's law. A gaseous mixture's pressure equals its component gases' pressures summed. Henry's law. A gas's solubility in liquid is related to its pressure. Hess's law. Changes in enthalpy are independent of the number of steps in the process. The law of combining volumes. Under constant conditions, ratios between the volumes of gases from reactions feature simple integers. The law of conservation of mass. Total mass in a closed system does not change during chemical reactions. The law of definite proportions. Samples of a substance have identical proportions of elements. The law of multiple proportions. Some reactions produce multiple compounds. The ratios of elements in them are simple integers.
Modern Chemistry, Chapter 11, Bonding. Chemical bonds are the forces that hold atoms together as molecules. There are 3 types of chemical bonds: covalent, ionic, and polar covalent. In a covalent bond, atoms share 2 or more electrons. An ionic bond involves one atom losing an electron to another. Oxidation numbers refer to how many electrons an atom loses in such a bond. In a polar covalent bond, electrons are shared unequally, but are not lost to the other atom. Thus, it resembles both covalent and ionic bonds. Which type of bond two atoms will form depends on their electronegativity. Some compounds are defined by the bonds that unite their atoms. For instance, covalent compounds are compounds with covalent bonds. Various factors define chemical bonds and molecules. For instance, a bond length is the distance between a bond's atoms. Bond energy is the energy required to break a bond. The number of bonds two atoms share is their bond order. The distance between a molecule's charges defines its polarity and dipole moments.
Organic molecules in the real world. The study of organic molecules has many real-world applications. Hydrocarbons, the main components of petroleum, are very important. Alkanes, or saturated hydrocarbons, are present in crude oil and natural gas. Simple alkanes, such as propane, are burnt as fuel. Products like petroleum jelly and paraffin wax use complex alkanes. These alkanes have multiple geometric isomers. The chemical properties of each isomer differ from the others. Such differences may be small, though. For instance, a cis isomer and a trans isomer may only differ in boiling points. Alkenes and alkynes, the unsaturated hydrocarbons, also have various uses. However, unlike alkanes, they can be somewhat rare. One way engineers produce alkenes is through petroleum cracking. Aromatic hydrocarbons, such as benzene, are used in high-performance fuels. Engineers use reforming reactions to produce aromatic compounds from alkanes. Pure carbon molecules also have potential uses. For example, fullerenes, like nanotubes, are incredibly durable. Thus, they may be used to create high-strength fibers.
www.smithfieldchemicals.com/functional groups. Our functional groups. Here at Smithfield Chemicals, we think quality matters. That's why we specialize in specific sets of functional groups. Halides. Alkyl halides can be formed by reactions between free radicals. However, we prefer to add chlorine directly to carbon-to-carbon double bonds. Hydroxyl. We use hydroxyl groups to manufacture various chemicals. The groups can attach to tetrahedral carbon atoms to create alcohols. They can also attach to aromatic rings to form phenols. Ethers. We also specialize in ethers. Condensation reaction featuring ethanol and sulfuric acid produce diethyl ether. Carbonyl, carboxylic acids, and esters. Attaching a carbonyl group to two hydrocarbon radicals creates a ketone. Attaching it to a hydrocarbon radical and a hydrogen atom creates an aldehyde. By oxidizing aldehydes, we form carboxylic acids. They then react with alcohols and phenols to produce esters. Through such processes, we can create artificial triglycerides. Amines and amides. Through hydrogenation, we can turn nitro compounds into amines. With further hydrogenation, we can turn amines into amides.
Transition metal bonding. Chapter review. Chapter 1. The participation of d electrons in bonding and chemical reactions is important. It largely determines the properties of transition metal compounds and coordination complexes. Molecular orbital theory describes bonding in transition metal compounds and coordination complexes. Delta bonds are more important to transition metals than main group elements. Overlapping metal and ligand orbitals create molecular orbitals. Chemists use specific terms to describe the formation and filling of such orbitals. They include ligand to metal, L to M, sigma donation, ligand to metal, L to M, pi donation, and metal to ligand, M to L, pi donation. M to L pi bonding is also known as back bonding. Dative bonds coordinate metal atoms or ions to ligands in coordination complexes. They form various symmetrical arrangements. Crystal field theory accounts for the properties of coordination complexes. In octahedral complexes, the degenerate d orbitals split into two levels. The difference between them is called crystal field splitting energy, delta O. The delta O determines the complex's magnetic properties. Large values of delta O create low-spin complexes. Conversely, small values of delta O create high-spin complexes.
The phase transitions of water. Like many substances, water can exist in three phases. The phase depends on the surrounding temperature and pressure. A phase diagram can illustrate such conditions. The solid form of water is called ice. Freezing liquid water forms ice. At sea level, the melting point of ice is 0 degrees Celsius. At this temperature, ice goes through a phase transition and becomes liquid water. Liquid water can become a gas by boiling or evaporation. The boiling point of water is 100 degrees Celsius at sea level. However, water evaporates into water vapor at lower temperatures. When water vapor touches a cool surface, it can undergo condensation. This turns it back into a liquid. Water sometimes performs other phase transitions. For instance, ice can become water vapor directly through sublimation. Similarly, water vapor going through deposition directly into ice causes frost. At 0.01 degrees Celsius and 611.73 pascals, water achieves its triple point. At its triple point, water exists as a solid, gas, and liquid at once.
Results of ammonia synthesis experiment. We performed the following experiment to produce ammonia, NH3, from its component parts. We wanted to observe the synthesis process itself and evaluate the efficiency of our methods. Please refer to page 17 for the precise details and formulae of our experiment. Ammonia has many practical applications. For instance, a solution with ammonia as a solute and water as a solvent creates household ammonia. When mixed correctly, this solution will not form a precipitate. Household ammonia is used in cleaning products and features a 5 to 10% concentration of ammonia. The reactants in our experiment were nitrogen, N2, and hydrogen, H2. When measuring our reagents, we used 3 times as much hydrogen as nitrogen. More would have been in excess of what was needed to create the product. Since our reaction was balanced, both reagents could be considered limiting reactants. To start the reaction, we used a magnetite catalyst. Our experiment was a success. The hydrogen and nitrogen effectively combined to form ammonia. The actual yield of our reaction was only slightly below our theoretical yield. In fact, the percentage yield was over 97%. Our method of ammonia synthesis proved to be highly efficient.
Chemical reactions. Chemicals react in many ways. Some reactions can be classified in several ways. See the list below for examples. Reaction: formation of iron 2 sulfide. Types: synthesis: simple elements to form a complex compound. Addition: no additional products are produced. Solid state: occurs between two solids without a solvent. Equation: sulfur S8 plus iron 8Fe equals 8FeS. Reaction: electrolysis of water. Type: decomposition breaks up a complex compound into two simple elements. Elimination produces two simple products. Equation: H2O equals H2 plus O. Reaction: the reaction between hydrobromic acid, HBr, and sodium hydroxide, NaOH. Type: acid-base reaction, caused by the interaction of an acid, HBr, and a base, NaOH. Double replacement. The compounds exchange bonds. Precipitation: sodium bromide, NaBr, forms. Equation: HBr plus NaOH equals NaBr plus H2O. Reaction: the reaction between zinc and hydrochloric acid, HCl. Type: single replacement. Zinc replaces the hydrochloric acid's hydrogen. Substitution: it changes the compound's functional group. Equation: Zn plus 2HCl equals ZnCl2 plus H2. Reaction: the reaction between hydrogen and fluorine. Type: redox. The hydrogen experiences oxidation and the fluorine experiences reduction. Equation: H2 plus F2 equals 2HF. Reaction: formation of hydrogen chloride. Type: photochemical reaction. It requires light to occur. Equation: H2 plus Ci2 plus light equals 2HCl. Reaction: the reaction between ammonia and copper, 2 nitrate. Type: complexation. It forms a coordination complex. Equation: Cu2 plus Aq plus 4NH3 Aq is in equilibrium with CuNH3 4 2 plus Aq1.
Stoichiometry, Chapter 3.2. Stoichiometry is the study of the relationships between reactants and products in chemical reactions. Relationships between reactants are expressed as ratios in chemical equations. When the equations are in balance, the ratios are usually whole numbers. There are multiple branches of stoichiometry. Reaction stoichiometry deals specifically with the ratios of substances participating in reactions. Composition stoichiometry is primarily concerned with ratios between elements and compounds. Gas stoichiometry handles ratios in reactions that occur between gases. A branch called heat stoichiometry measures changes in heat during reactions. It can determine if a reaction will be endothermic or exothermic. Stoichiometry can be a very useful tool for chemical engineers. Chemists can use stoichiometry to determine amounts of reactants required to yield products. The stoichiometric ratio of a reagent refers to the ratio of substances needed for a reaction to occur completely. At the stoichiometric ratio, a reagent is completely consumed by a reaction without producing an excess or shortfall. If accurate stoichiometric ratios are used, reactions will leave behind no residue. Calculating stoichiometric ratios allows chemical engineers to design efficient chemical reactions. Depending on the nomenclature used, terms related to stoichiometry may be different. For instance, stoichiometric coefficients are also called stoichiometric numbers. Similarly, stoichiometric ratios are also referred to as stoichiometric amounts. Though they have different names, the values are the same.
Chemical equilibrium. In general, equilibrium refers to a balance between opposite forces. Chemical reactions reach conditions in which their component chemicals will not change further. Such a condition is known as chemical equilibrium. In general, chemical equilibrium is achieved through dynamic equilibrium. In a dynamic equilibrium, a reverse reaction occurs at the same reaction rate as a forward reaction. As reactants change into products, products also change back into reactants. The pressures and concentrations of reactants in a reaction in equilibrium are related. The ratio between these quantities is called the equilibrium constant. Spontaneous reactions sometimes occur in systems in equilibrium. A system's entropy determines the direction spontaneous reactions proceed in. Entropy is also responsible for determining the amount of Gibbs free energy that is available in a system. Gibbs free energy refers to the amount of useful work a system in equilibrium can produce. There are multiple other types of equilibrium. At phase equilibrium, two or more phases of a substance can exist simultaneously. For instance, at phase equilibrium, both liquid water and water vapor can exist together. When a system is at thermal, mechanical, and chemical equilibrium, it is in thermodynamic equilibrium. An isolated system in thermodynamic equilibrium will experience no change.
The importance of mass balance and perfect mixing assumption in engineering. Controlling mass balance is vital to engineering. This is particularly true with ammonia production. The Haber process of producing ammonia has a relatively small conversion rate. Because of this, engineers use mass feedback. They run the same material through the system multiple times. As mass flow exits the system, it is input back into the system in a cyclic process. A mass balance tells engineers how many times the cycle should repeat. Engineers can use mass balances in any situation, where components are both miscible and non-reactive. The perfect mixing assumption is also important to this process. Engineers can miscalculate conversion levels if they assume chemicals are perfectly mixed. Mass balance is equally important in laboratory ventilation. Some toxic substances have high rates of dispersion. Because of this, the air in labs must be replaced regularly. To determine how often the air needs to be replaced, engineers again use a mass balance. Mixing assumptions should be verified to prevent accidents or injuries. Likewise, mass balances are important in pharmaceutical manufacturing. Pharmaceutical companies often manufacture drugs out of granular materials. Mass balances let them ensure proper dosages. If the density of substances in a dose is incorrect, a patient could receive a deadly or ineffective dose.
Membrane separation in you. Why membranes are important. Membrane-based separation is important to many purification processes. For instance, reverse osmosis operations are often used in the filtration of seawater. By creating better membranes, these separation processes can be improved. One process open for improvement is hemodialysis. When a person's kidneys fail, mechanical assistance is needed. In this dialysis process, harmful species of molecules are removed from the bloodstream. The raffinate in hemodialysis is blood with unwanted substances in it. The permeate that remains after filtration is blood without toxic and waste substances. One of the main components of the permeate is urea, which removes nitrogen from the body. Hemodialysis often functions by pumping blood through hollow fiber membranes. These membranes are tube-shaped and have pores on the sides. As a result, they are semi-permeable. The membranes remove unwanted substances, while the cleansed blood returns to the body. Although people use hemodialysis regularly, it is far from perfect. There are multiple areas for improvement. One area that can be improved is the permeability of membranes. Better membranes could reduce the amount of unwanted substances in the permeate. Unfortunately, as the effectiveness of membranes improves, the surface area required increases exponentially. Correcting this problem is one possible area for further study.
From J. Freeman at chemicronlaboratories.com to S. Gordon at progressivecapitalinvesting.com. Date, May the 19th. Subject, CSTRs. Dear Mr. Gordon, I am writing you to request funding for a new project. I would like to install a couple of CSTRs, continuous stirred tank reactors, in my lab. CSTRs are reactors that constantly stir the contents of their tanks using impellers. These reactors would aid me greatly in my research. They are designed to ensure proper mixing. As such, I could easily calculate various values, such as the residence time of the reactor's contents or the reaction rates of first-order reactions. There are other benefits as well. For instance, the reactors I want maintain a constant temperature. This ensures that reactions are isothermal. Additionally, the reactors can mix both liquid solutions and slurries. Furthermore, I will be able to connect them to the separators already installed in my lab. In fact, I plan to connect them all in such a way that effluent will flow from each machine to the next. By organizing it like this, I will not have to recover the unconverted reactants from the product stream. A sequential setup will also be the most economical. It should have a relatively low capital cost. Plus, I will not need to adjust the throughput often. As a result, the operating cost will also be low. Thank you. Dr. Janet Freeman, Chemicron Laboratories.
Smith Scientific Equipment, plug flow reactors. Frequently asked questions. What is a plug flow reactor? A PFR, plug flow reactor, is a chemical reactor that is shaped like a tube. Reactants mix and react as they are pumped down the tube. PFRs are also known as tubular reactors. What are plugs and plug flow? Plug flow is a model that describes the velocity of fluids flowing through a pipe. The model uses plugs, which are imaginary units of the fluid that are infinitely thin. What are the characteristics of PFRs? PFRs are generally used to perform single first-order reactions that are irreversible. These reactions usually occur in a steady state. As reactants travel down the pipe, they create a gradient. At one end of the gradient, little chemical reactions have occurred. At the other, much more reactions will have taken place. The reaction's reaction rate can be calculated using the Arrhenius temperature dependence equation. Reactants can be added to PFRs at multiple points, which can improve the efficiency of a reaction. Unfortunately, reaction of PFRs cannot reach 100% completion. Because of this, distillation is often used to remove unconverted reactants from the product. Are PFRs catalytic reactors? Yes, some PFRs are catalytic reactors. Their reactors are packed beds that are filled with a material that acts as a catalyst for the chemical reaction.
Chemtech International, Chemical Manufacturing Equipment, Product Listing, Batch Reactors. Chemtech offers a wide variety of batch reactors with customizable options. Each of our reactors features our patented agitator and baffle assembly. This ensures proper mixing of your products without creating disruptive flows. Reactor options. We offer 3 different types of batch reactors. The first option is for a true batch reactor. It seals when the reaction begins, and substances cannot be added or removed while the reaction is in progress. The other 2 options are both semi-batch reactors. These reactors allow the addition or removal of materials after the reaction starts. Our continuous batch reactors will allow you to add or remove material continuously during the reaction. Alternatively, our fed batch reactors allow you to add or remove materials at intervals. Cooling jacket options. We provide 3 options for cooling jackets. These will allow you to control the temperature inside your reactor. We ensure the stability of all of our cooling jackets. Our simplest cooling jacket is a single external jacket. This jacket has the simplest design and also a low price tag. Our half-coil jacket provides a greater degree of control. This jacket has greater temperature uniformity than our single external jacket. Our best cooling jacket is the Coflux jacket. It provides maximum temperature uniformity to your reactor.
Janet Smith, Director, Andersonville Water Authority, 2413 Main Street, Andersonville, Maine, 15112. Dear Janet Smith, Andersonville's current wastewater treatment facilities are severely outdated. I have several suggestions for improvements. Our current facilities separate wastewater mechanically. However, there are many ways that we could use microorganisms to clean it. All we need to do is isolate wastewater with a large biomass of microorganisms. This could be a bioreactor. Or it could be an open location, such as an aeration basin or an oxidation ditch. We would need to provide some way of aerating the wastewater. After all, the microorganisms will not break down contaminants unless their BOD is met. Additionally, if we use a bioreactor, we may need to find a way to make a moving bed out of the sewage. Then, we simply need a submersible mixer to mix the flock, the microorganisms, and the air bubbles. This creates an activated sludge, which will break down organic pollutants. Alternatively, we can use a method in which the sewage acts as a fluidized bed. This would allow us to simply run it over a surface like a trickling bed. We could also run it through a membrane bioreactor, such as a rotating biodisc tank. Let me know what you think. Sincerely, Dr. Philip Bakersfield, Biochemical Engineer.
Chemical engineering applications. Chapter 8. Interfacial mass transfer between two-phase systems. In many cases, chemical engineers can use homogenization to make the matter in a system a uniform phase. However, this does not always work. Sometimes chemical engineers have to deal with two-phase systems. When this happens, they use specific unit operations to transfer mass across interfacial boundaries. There are two operations that can be used in solid-liquid systems. When chemical engineers need to transfer mass from a liquid to a solid, they use adsorption. To achieve the opposite effect, they use solvent extraction. Chemical engineers can also use adsorption in a solid gas system. This allows them to transfer mass from a gas to solid. However, to transfer the mass from the solid to a gas, they must use desorption. In a liquid gas system, absorption allows chemical engineers to move mass from a gas to a liquid. Desorption, or stripping, achieves the opposite effect, transferring matter from a liquid to a gas. Finally, there are two operations chemical engineers can use in liquid-liquid systems. They can use distillation to separate chemicals by boiling. Alternatively, they can use crystallization to do it through freezing. When two immiscible liquids exist together, the dispersed phase is the one contained within the continuous phase.
Novatech Chemical Plant, Employee Manual, Chapter 4.2, Equilibrium Stage Processes. Equilibrium stages are zones in which two phases are in equilibrium with each other. When two phases are mixed together, their chemistry can partition some components into specific phases. This can enrich one phase with a substance while depleting it from the other. To isolate the phases with the desired components, we perform equilibrium staged processes. Flash distillations are processes that separate liquid and vapor components of a mixture. Flash leaching involves solid and liquid phases. Flash extractions occur between two liquids. We perform flash distillations in vessels that are referred to as flash drums or knockout pots. These are basic vessels in which we can control temperature. We use flash calculations to calculate the effectiveness of our equilibrium stage operations. However, the ideal effectiveness does not always match the actual effectiveness. The ratio between the real and ideal values is known as the stage efficiency. Please remember, our goal is to have the ratio as close as 1:1 as possible. Since our stage efficiencies are not perfect, we line up stages in sequence. So, we feed streams through multiple vessels, in what is known as a cascade. There are three arrangements we can place equilibrium stages in: co-current, countercurrent, and cross-current.
Chapter 17. Energy Balance and Heat Exchange. The energy balance of a system can be affected by multiple factors. A moving system's kinetic energy can affect its energy balance. Its potential energy can also have an effect as well. Another factor that affects a system's energy balance is work occurring around the system. For instance, the shaft work performed by a system's mechanical parts can influence its energy. Similarly, the expansion work caused by mass flows entering the system can affect its energy. In fact, the system's enthalpy equals the system's expansion work plus its internal energy. It is worth noting that some systems are rigid and cannot receive expansion work. An additional factor that affects a system's energy balance is heat exchange to and from the system. Substances flowing through the system can affect its heat, as can processes inside the system. The heat capacity of a system can be determined by the specific heat of its materials. Heat capacity is generally measured in joules per Kelvin. However, it is sometimes measured in older units like calories and BTUs. Some systems such as insulated systems, are adiabatic. This means that they do not transfer heat to or from their surroundings.
Chemical engineering: yesterday, today, and tomorrow. Chemical engineering led to many advances over the last century. One of the first major advances came in the 1940s. Developments in biochemical engineering allowed for medications to be mass-produced. During the 1950s, progress was made in the study of polymeric materials. The result was an explosion in the applications of plastics. Since the 50s, materials have decreased in toxicity and become more recyclable. Additionally, engineers have become better at removing impurities from substances. But many agree that plastics remain the most recent major breakthrough in the field. However, chemical engineers are working in two areas that could change that. The first is tissue engineering. This field is devoted to creating bodily tissues. It may one day lead to people being able to regenerate lost organs and body parts. Currently, scientists are working on improving the scaffolds on which artificial tissues grow. The other field of chemical engineering that could affect the future is nanotechnology. Nanotechnology allows people to manipulate matter on a molecular scale. Though it may be some time before people can build items from atoms, colloid science has already produced useful, nano-sized materials. Additionally, scientists have been able to build chemical sensors which can detect very small quantities of chemicals.
South Central State University. Chemical engineering career options. Graduates with degrees in chemical engineering have a wide variety of career paths to choose from. Some become professors and pass on their knowledge. Some go on to become researchers at labs. Many graduates use their knowledge of chemical engineering to help solve environmental issues. One way a chemical engineer can do this is by working on renewable energy. For instance, a chemical engineer can work on photovoltaic cells that harness solar energy. Other chemical engineering graduates become advisors. Many organizations in both the public and private sectors need people with knowledge about chemistry and the biosciences. A chemical engineer could help government officials determine public policy on issues concerning chemical engineering. He or she could even conduct investigations to ensure that chemical engineering processes are safe. Of course, corporations that produce chemicals always need chemical engineers. There are a variety of roles that a graduate can fill at such a company. Design engineers are needed to design the chemicals the company will produce. However, before the company can create them, manufacturing engineers must design the production systems that will be used. Finally, sales engineers are often vital for selling the chemicals to customers.
AVN Pharma Education.